Hello, everybody. This lecture, I'm going to follow the radiation chemistry, and I go with this one that if you're dealing with nucleus, that it has N or Z, number of neutrons or protons, equal to 2, 8, 20, and 28, 50, 82, and N, okay, and N 126. If you have a nucleus that has Z or N equal to this number, that nucleus, it will be a stable nucleus. Otherwise, it will go through radiation, and it will do, decades, will go through nuclear reactions, and it will turn to other isotopes or species. And we said rate of that reaction, we can calculate it through K multiply N, where K is the rate constant, and N is number of radioactive nuclei. This is a first order equation, and because it's a first order first order reaction, and if you double concentration of N or number of N, rate is going to be 2 times faster. And the formula for first order is going to be ln of NT equal to minus KT plus ln of N0. This is integrated rate formula. Integrated rate formula for first order reaction. And this one is going to tell you after T time what will happen with N, how fast N is going to go down. You'll know it through the K. Next thing, you will know how much from N left after T minute or T hours or years. Okay, and we can rewrite this one as ln of N T over N0 is going to be equal to minus KT, and N0 versus NT. N0 initial number of nuclei, and this one is going to give us number of nuclei after T time. Okay, so I mentioned this one last time, okay, and we practiced this formula, and we said T half-life is the time that we need to spend to drop N to half of initial number of nuclei, and the T half-life we can calculate it through this formula is 0.693 over K. Or K is the rate constant. Now, rate is equal to K multiply N. So I can say rate at the beginning is going to be equal to K multiply N0, and rate after T time is going to be K multiply NT. Okay, if I know number of nuclei after T time, I will put it inside here, inside this formula. If we call this one 1, that one is 2, call this one 3. Put the n, whatever left from n, inside number 1, and it's going to give you the rate. But the rate that you get this time, you call it rate T time, because rate after T time is going to go down because n is going down. Okay, so let's use this formula, ln of nt over n0 equal to minus kt. But we need to know the nt. Okay. So from number 2, n0 is going to be rate 0 divided by k. And from number 3, you can say nt is going to be rate t divided by k. So now I go with fit this formula, let's call it 4. Fit number 4, we get ln of rate t divided by k, and hold this one divided by rate 0 divided by k equal to minus kt. You cancel k by k, you get ln of rate t divided by rate 0 equal to minus kt, and I'm going to call it 5. So if I have rate of different reactions, I can compare them, divide them, and I can get idea about k, or I can get idea about the time. Okay, and here let's do example about it. We have a bone that belongs to a human being, and it has carbon 14. And the decay rate is equal to 4.50 per minute. Disintegration per minute. Okay, so that's a rate, decay rate for it. Okay. The next thing that we have, it says if a living organism has a decay rate of, so if the living has a decay rate of, this time I'm going to write it here, 15.3, and is disintegration per minute. Okay, and it says 15.3 disintegration minute per disintegration divided by minute multiply gram of carbon. Okay, so now the question is going to be, it says, how old is this human being, or that actual bone? How old is that bone? So we are looking for this. We go ln of rate after T divided by rate after, or rate at the beginning is going to be equal to minus KT. We are looking for T. We want to find T. In order to find T, we need to have a K. Okay. The way you find K, you say T half-life is equal to 0.693 divided by K. So K is going to be equal to 0.693 divided by T half-life. Okay. Now this is carbon 14. Because it's a carbon 14, we know the half-life for it. T half-life for carbon 14 is equal to 15 year. So K is going to be 0.693 divided by 15 year, and the answer is going to be equal to 1.213 multiply 10 to the power of minus 4 year minus 1. We have 3 sig fig, here 3 sig fig. Okay, so now we got the K. Now that I have the K, I put it inside this formula and I will calculate T. So I go with ln of rate 2 or T divided by rate 0, and the K we have it equal to minus, is going to be 1.213 multiply 10 to the power of minus 4 year minus 1 multiply T. Okay, so T, it will be whole this one divided by K. Okay. So ln of, let's define the rate 2. Rate 2 is equal to 4.50, and is this integration per minute. This integration per minute. And next one, we have it 15.3 this integration divided by minute. Okay. So both of them actually comes with this integration per minute multiply gram of carbon. So you can write here gram of carbon for both. But it doesn't matter. They will cancel each other. And this divide by minus 1.213 multiply 10 to the power of minus 4 year minus 1. And the answer at the end, it will be 1.0 multiply 10 to the power of 4, and unit is year. Okay. So it's around 10,000 year. Okay, 10,000 year old. Okay, this is one way, is a one way actually to use the rate of different reactions or different nuclear reactions or processes. I had I had the rate for an ancient bone. I got, we have the rate for it. The rate, it says 4.50 disintegration per minute and multiply gram of carbon. And for live organism, it's around 15.3. You get the ratio between them. Now that I got the ratio divided by K, it will give us the age of that bone. Okay. Let's practice another example. And we have, say, rock or stone, I go with medium. That it has 0.556 gram of lead 206 in every 1 gram of uranium 238. Okay. T half-life for uranium 238 is equal to 4.5 multiplied 10 to the power of 9 year. So 4.5 billion year. Now, question is gonna be, let's assume at the beginning there was no lead. There was no lead in this species. Tell us how much uranium we started with and how much time we spent, to get this gram of lead. Okay, I need to remind you about this. That's uranium 238. At the end, it will turn to lead 206. So it's not stable. Okay. You go with this. T half-life equal to 0.693 divided by K. So K equal to 0.693 divided by T half-life. And the T half-life is equal to, whereas the T half-life is 4.5 multiplied 10 to the power of plus 9 year. And that's going to give us the K, which is 1.5 multiplied 10 to the power of minus 10 year minus 1. This is really low process. Okay. Now, if I know how much mass from lead I have, I will use the ratio between them, which is 1 to 1, and I will get a gram of uranium. It says we have 0.556. So we have that, okay, that number of gram of lead Pb. We have it. So I'm gonna divide this one by the molar mass, which is 206, equal to 1 mole of lead, and 1 mole lead equal to 1 mole uranium, and 1 mole uranium equal 1 mole uranium equal to 238 gram of uranium. So the mass that we need to start with to get 0.556 gram of lead is going to be equal to 0.642 gram of uranium. We need to start with this. Okay. Now let's get back to this part. It says in every 1 gram of uranium, we have that amount of lead. Remember, if you pick 1 gram of uranium and you find 0.556 gram of lead in it, that means you had more from uranium. Some of it was converted to lead. So the initial mass of uranium is going to be whatever you have here, which is 1, and plus this number. So if you start with 1.6 gram of uranium, you will get that number. You get 0.556 gram of lead. Okay. And here, like I need to, like I need kind of like emphasis on this one. This one, it says in 1 gram of uranium, we have that amount of, we have 0.556 gram of lead. After T time, okay, after T time. So what was the initial mass? Initial mass is going to be equal to 1, whatever left or whatever we have right now, which is 1 gram, and whatever we lost, which is 0.642. So the initial mass is going to be 1.642 gram of uranium. And the current is going to be 1, okay? Current, it will be 1. So you call this one NT, and 1 plus 0.642 is going to be N0. So let's define N0 and NT. N0 is going to be equal to 1, whatever we have right now, plus whatever we lost, and NT, right now we see 1 gram. So you go ln of NT over N0 equal to minus KT. So T is going to be minus of ln of NT over N0 divided by K minus of ln of N0. Now NT is 1 and N0 1 plus 0.642 divided by K, which is number for it is 1.5 multiply 10 to the power of minus 10 here, and T, it will be equal to 3.2 multiply 10 to the power of 9 here. Okay. So this is the second example about using, the first order formula to calculate the age of one, radioactive compound, or say like, age of one ancient object. Okay. So now I will switch to fission. If you go with uranium 238 and you bombard the uranium with neutron, you can break it down through generating one unstable isotope. This isotope, it will turn to 239 and 93 plus a beta. Okay, so we added something to it. Now we turn it to another species. Okay, so this one is going to be new species that we generated. Okay, and if you do it with here uranium, go uranium 235 and you add neutron to it, you will get barium, plus krypton plus 3 neutrons plus energy. Okay, plus a huge amount of energy. Okay, so if I go with good amount of uranium and treat it with neutron, I can generate huge amount of energy. Okay, and the funny thing, like check this one, you start with only one neutron, but now you generated 3 neutrons. And those 3 neutrons, now they can run 3 of these reactions. So 1 neutron is enough to spread, the reaction and make it, 3 times faster. If I start with 2 neutrons, I'm gonna get 6 neutrons. And now 6 neutrons will run 6 new nuclear reactions, and we get, 6 times energy. We call this one chain reaction. This is very common when it comes to nuclear reactions. Okay, and they use this one in nuclear bomb. So you need to have enough mass from uranium. If you have enough mass from uranium, you treat it with with a neutron, and it's going to give you a huge amount of energy, and that energy can destroy anything. Okay. We call this one here. So this type of reaction, we call them chain reaction. But what we did here, we broke down the uranium to different species, so I can call it, nuclear fission. Okay. So nuclear fission is a reaction that you start with one species, you treat it with something else, and you break it down to smaller species. We had uranium-235, but right now all species that we got, they're way smaller. We broke it, okay? We broke it. Because we broke it, we call it nuclear fission. Okay. Now, I will start subject that is related to Albert Einstein or Einstein formula. And a formula that he came with, it says E equal to mass multiply square of velocity of light. So m, mass in kilogram, and c is velocity of light, and it has unit of meter over second. Okay, meter over second. Or is you want to use a precise number, it will be 2.9979 multiplied 10 to the power of 8. If you round it, it's a 3. Okay. Why we want to go through this formula? Let's start with this subject that we call it mass fact. Okay. I want to go with this one, and also the second one is going to be nuclear bonding energy. Okay. Okay. So let's go with uranium 235 92 plus 1 neutron. Okay. See what we get. We get barium is 140. Plus K krypton 93 36 plus 3 neutrons. Okay, if you add the masses on the left side, okay, mass of uranium plus mass of neutron, the total mass is equal to 236.05258 atomic mass unit, and for the right side, total mass is equal to 235.86769 atomic mass unit. As you see, these two numbers are not equal. Okay, so now if I go back to balancing, we said when we balance any chemical reaction, we assume that the masses on both sides, reactant and the product, are the same. Okay, when you add the masses, they're the same, but right now they are not. This one is a 236, on the right side is 235. So the question is going to be, what's happened with the energy? Okay, and when we get that one, we use the Albert Einstein formula, and we will calculate how much mass we have lost, and that mass we can calculate through energy. Remember, this nuclear reaction is going to give you energy, and you have to focus on this energy and see how much mass you lost as an energy. If you have this energy, then you put it inside this formula and you'll calculate the mass. So you go with this now. Mass loss is equal to 236.05258 minus 235.86769, and the answer is 0.18489 atomic mass unit. So mass loss is equal to this number, atomic mass unit. We can transfer this one to kilogram. Okay. One atomic mass unit is equal to 1.66054 multiplied 10 to the power of minus 27 kilogram. Okay. So I will say mass loss, you go with the difference, multiply the mole ratio, so the ratio between atomic mass unit and kilogram. Cancel atomic mass unit by atomic mass unit, and the answer is going to be mass loss equal to 3.0702 multiply 10 to the power of minus 28 kilogram. Okay, I had to transfer this one to kilogram. Why? Because this formula energy equal to mass multiply square of velocity. M comes with kilogram unit, so we need to have the mass loss in kilogram. And now we go with this. Energy is equal to mass loss, which is 3.0702 multiply 10 to the power of minus 28 kilogram multiply 2.9979, or 3.00 multiply 10 to the power of 8 meter over second. This is going to give us energy in joule. Okay, so now we have the energy in joule. Okay, this energy will be released whenever, okay, whenever we start with one nucleus of, okay, one nucleus of uranium-235. Okay, just one. If you wanted to calculate the amount of energy per mole, because usually in chemistry we go in joule or kilojoule per mole, then you have to multiply it by Avogadro. This number, it looks, is a small number, but when you multiply it by Avogadro, and you will see that, you know, it's going to be a big deal. So here, energy, it will be 2.7593 multiplied 10 to the power of minus 11, and this is joule per, okay, one atom of uranium-235. So you say this time you want to know, and you want it in mole, you go with Avogadro number. Equal to 1 mole. So the answer will be 1.6617 multiplied 10 to the power of 13. This time plus 13 joule per mole of uranium-235. This number is a huge number, okay? Huge number. Okay. So we're talking about, okay, 1 mole of uranium-235 will give us around 1 billion kilojoule energy. Okay. And you're talking about 235 gram. 235 gram of uranium will give you that amount. It's less than a pound. It's half a pound. Half a pound, you get 1 billion kilojoule energy. This is a really, really huge number. Okay. So whenever we do a fusion, when we break down, you know, when we break down like a radioactive compound, we get energy. Some of the mass will be transferred to, you know, energy. And if you want to follow law of conservation of mass, you have to say, when it comes to nuclear chemistry, nuclear reaction, mass, it will be constant if you add energy that was emitted to the whatever left as a mass, and then mass, it will be constant. Otherwise, it's not going to be a constant number. Okay. Next one that I'm going to focus on, it said mass, fixed, and binding energy. Okay. Go with this. 2 hydrogen, and add 2 neutron to it. You will get helium. You get helium. If you add the masses, on the left side, mass is equal to 4.03298 atomic mass unit, and the right side is 4.00260 atomic mass unit. Okay, so we started higher mass, we got lower mass. Question is, what's happened with the energy? Where does that, what's happened with the mass? Where does that energy or mass go? Okay. So I'm going to say we have a mass loss and is equal to whatever left So whatever left is 4.00260, and this is the initial one. Okay. Initial one is higher. So if I subtract the final mass from the initial, I will get the difference between them. Okay. So I will subtract the whatever left from the initial mass. Okay. This is initial mass, and leftover is 4.00260, and the answer is 0.03038 atomic mass unit. Okay. So what we did, we had 2 hydrogen atoms. We added 2 neutrons, and we got only 1 hydrogen, 1 helium. Okay, so here we have 1 proton, we have 2 protons, and then we have 2 neutrons. So 2 protons plus 2 neutrons, we get 2 protons and 2 neutrons, and we want to put them inside nucleus. So we want to put 2 protons and 2 neutrons. We will have outside with 2 electrons. I want to keep neutrons and proton inside the nucleus. So there must be a glue or like binding force to keep the 2 protons and neutron inside the nucleus. And that one we call it nuclear binding energy. You're going to spend some mass, you will turn it to energy, and you will use that energy to bind, okay, to bind actually the species. Okay, that amount of mass we lost, okay, and I'm going to turn this one to energy. So I'm going to say nuclear binding energy is equal to 0.03038 atomic mass unit. 1 atomic mass unit, if you want to write it, in electron volt, okay, if you write it in electron volt, is going to be equal to 931.5 mega electron volt. Answer is going to be equal to 28.30 mega electron volt. Okay, so that amount of energy we need to spend to put the protons and neutrons inside the nucleus and keep them close to each other. Okay, in physics, opposite of chemistry, we use electron volt. Use the electron volt, and we show it by here, and EV, okay, to to talk about the amount of energy. So barely they talk about joule. They want to go like with electron volt. And when you say M EV, you mean mega electron volt, mega electron volt, and this is going to be equal to 1.602 multiply 10 to the power of minus 13 joule. Okay. So that amount of energy we need to use as a binding force or binding, nuclear binding energy to keep the two protons and two neutrons. But now, can we, compare binding energy of, for example, different nuclei? And the way we do it, we need to divide, this amount of energy per, number of neutrons and protons. Otherwise, we cannot compare, for example, carbon with helium, because carbon has 6 protons and 6 neutrons, while helium has only 2 protons and 2 neutrons. So here we say binding energy per 1 neutron or proton nucleus is going to be equal to binding energy divided by number of protons and neutrons. So for helium, binding energy will be, we have the binding energy equal to 28.30 mega electron volt. We have 4 protons and neutrons. And this one, it will be equal to 7.075 mega electron volt. So binding energy per neutron for helium is equal to 7.075 mega electron volt per 1 proton or neutron. For carbon, binding energy per nucleon is equal to 7.68 or 680 mega electron volt per nucleon. Okay, this is carbon. Okay, when you compare them, you see for carbon the number is bigger. Because it's bigger, that means carbon atom is more stable than helium. Okay, so carbon stay as it is, but helium, it can get converted to something else. Okay. I think I'm going to stop the lecture here. Thank you guys. Appreciate for your time.